Everybody, thanks for tuning in today. I'm excited to introduce our seminar speaker this week, Dr. Jacob Adler, who's actually going to be my new postdoc here at Georgia Tech in the School of EIS. Jacob is a planetary geologist, and his research focuses on understanding past environments of planetary bodies, mainly Mars and the Moon. He also studies the dynamics of asteroids and impacts as well. And he commonly employs a variety of techniques from remote sensing to lab experiments. He received a bachelor's in geophysics and space physics from UCLA. He then went to the Arizona State University for his PhD, where he worked with Jim Bell in some of the research he'll be talking about today. After finishing his PhD in 2019, Jacob went to Johns Hopkins for a postdoc. And as I said, he's just started a postdoc here at Georgia Tech. Technically yesterday, so he's brand new. And today he'll be sharing with us some of his research into Martian deltas. And so Jacob, welcome to Georgia Tech, and take it away.
Thank you. Thanks for that introduction. And also it's great to be here. I'm looking forward to in person, maybe one day, meeting everyone as a postdoc in the department. So thanks for inviting me to give this talk. So the topic that we're going to cover today is deltas on Mars. And specifically, I'm going to show you examples of two of them, Jezero and Hypanis. So Jezero, you've probably heard a lot about already. I understand that there was another presentation also about Mars 2020, about Perseverance exploring Jezero. So we'll keep that at a high level. And then we'll talk about another delta that I researched during my PhD called Hypanis. So first, before we dive into deltas, we're going to cover a little bit why they often appear as landing sites. What makes them good candidates for Mars missions? Why have they historically been some of the paleo environments that have been selected? And then I'm going to cover a little bit about why possibly I think Jezero was selected, why the community thought that it met a lot of the criteria. And then finally, I'm going to ask this question of, is Hypanis also a delta? Because if it is a delta, then it has some big implications for all of Mars. So let's also talk about the history of water on Mars. You might have read some sensational news articles recently about such and such discovers water on Mars, and I see them about once a year. They're really great, but I want to point out that a lot of these discoveries are incremental, and we've known about large volumes of water on Mars for a long time. Some of the earliest telescopic observations on Mars, you can clearly see ice caps near the poles. We've seen valley networks from the time of Mariner 9, same as outflow channels. And so if some of the hypotheses for how valley networks form are either, snow melt or widespread precipitation, for example, and with outflow channels, these mega floods, so enormous catastrophic floods that went from the highlands towards the lowlands, possibly filling, this northern hemisphere of Mars. And so we've known about large quantities of Mars for a long time. We've seen surface frost, and even with the Mars, with MSL, we've landed on, a lake and river sediments. And so water is going to play a key role in future environments that we study, both in this Mars 2020 rover, where we're going to a river delta, but also in the future. NASA has this long-term vision of around 2035, let's say, putting humans on the surface of Mars for a mission. And so that human mission would, undoubtedly need water, both for human survival to drink, but also for creating fuel and studying astrobiology. So water is a key component. Now, one of the big debates over the inventory of water on Mars still revolves today around whether there was an ancient northern ocean. And so this topic hasn't been settled. But I would say that most of the debate today is not whether Mars could have had an ocean, but really when did it have an ocean, for how long, if it did, the location, precise location, and whether it was water or mostly ice. So that's what most of the debate revolves around today. If we back up and just look at how these deltas form, that'll lead us to understand why they might be good candidate environments to look at. And so, in a nutshell, this cartoon shows how river deltas form, with the Mississippi as an example. And so a river enters a standing body of water, and when it does that, then the flow is no longer confined to its channel. And so as the width of that flow increases, there's a decrease in velocity, and sediment drops out of suspension. And over time, this can build up a single, deltaic lobe, as is shown in the figure on the left. So, for example, the current lobe being formed on the Mississippi is in one location, but over time, the avulsion node, or where the sediment is moving back and forth, can shift. And so, for example, if the river breaches its natural levees, like during a flood, then it spills out onto a new course. It finds the topographic low or depression that's easiest to get to, and we have avulsion node migration. And avulsion node migration is one of the diagnostic features that is used to tell if something is a delta or not, especially from just remote sensing images, where it's often hard to get on the ground and tell. Now, what makes these systems good for biosignature preservation and biosignature formation to begin with? That's due to a few properties of deltaic systems. The first is rapid deposition. And so basically, if there were organic matter, you can entomb it by rapidly burying it in sediment. And then, at least for the terrestrial cases, deltas also provide this steady stream of mineral nutrients. And then finally, deltaic environments are sort of a buffer from the outside world, where there's reduced potential for destruction from high energy fluid flows, since these are formed in these low energy environments, again, which are rapidly buried. And so because of some of these reasons, one report known as the Summons et al. Report, so a paper by Summons et al. In 2011, has looked at different early Mars environments and tried to compare which ones would be the best for biotic matter formation, organic matter concentration, and organic matter preservation. And so you can take this report with a grain of salt, because there are so many different, astrobiologically relevant paleo environments that were believed to have existed on Mars or might be relevant. But at least from this one study, they found that the deltaic environments have a high potential in three of these categories: for formation, then later concentration, which happens most easily seen in the bottom set beds, which are the finest beds farthest from the delta apex and most easily accessible to the rover. And then finally, for preserving these organic matter components, if they ever existed. So here's an example of what a delta looks like on Earth. And if we were to dissect that and look at a cross-section, you can see that there's three main components. There are these top set beds, which are roughly horizontal. There are four set beds, which are more steeply sloping. And then finally, bottom set beds, again, the farthest out from the delta. And that's because the finer, lighter weight class are able to travel farther before settling. And so again, NASA has literally followed the water for decades in some of their missions, and this is spelled out in the image in the bottom left. but you could also see how water is still going to be playing a role in future missions. So paleoenvironments like lacustrine environments, think Gale Crater, hydrothermal, permafrost, all of these environments are going to remain relevant, at least for the time being. But it's also clear that they could be related to the best timing for life on Mars if we find these environments that are really old. And so we think life's best chance, if it started on Mars, was early. So that is when the dynamo was active in the first couple 100 million years. You have this magnetosphere providing extra protection, but also the climate could have been warmest and wettest. So here is a global map, elevation map of Mars. And what I'm showing in yellow squares is a survey of deltas, presumed deltas, from back in 2010. And so I'll show you an example of what one of these deltas looks like. This delta in particular is pronounced Eberswalde, which is from a German location. And it just looks enormously beautiful, in my opinion. You can see meanders, you can see scroll bars, you can see some of the features that I've already talked about, where bottom set beds could be accessible. If you were to land here, you would know already, based on the published literature, a sequence of events that you could drive up and measure to understand the fluvial history. Another canonical example is Jezero. And as we move to Jezero, I'll show you that on this plot, you might notice most of these deltas occur on the highland-lowland boundary. And so that could be significant. Several people have proposed that this is perhaps evidence of an ancient shoreline, how many of these deltas occur at the same elevation on the border of the northern lowlands. So moving over to Jezero, Jezero is found in this, large Isidis impact basin, but more precisely within the smaller Jezero crater. And Jezero is also a fantastic example because it's not covered by so much dust that you can't measure composition from multispectral images. And it has some of the most unique deposits on all of Mars, at least in terms of the larger region of carbonates that are present and other hydrated minerals and altered minerals that clearly show a history involving water and rock interaction. And so this is exciting that we're finally landing here. And I'll leave some of the finer details for another time because I'm sure we've covered that in previous seminars. But I do want to cover why was Jezero a strong choice compared to so many other landing sites. And I mean, perhaps one of the reasons is because it checks a lot of the boxes. And so not only is it good for astrobiology, but this is an example of the rubric that I helped create back in 2015 with the Mars 2020 team to try to put all the different landing sites kind of on the same scorecard. And it wasn't used for casting votes, but it was used to sort of pick apart the remaining questions that each landing site had. And from this rubric, you can see that we need to cache a certain amount of, different rocks for measuring different quantities, like ages of surfaces and astrobiologically significant materials in the caching. But we also want to know the broader context to a certain confidence level before landing at a certain site. And so this might be one of the reasons why Jezero is so strong, especially when you combine it with an extended mission. When it ultimately, back in 2018, when the sites were winnowed down to 4, 2 of those sites that were competing could be potentially merged together with this mega mission. So after the first year and a half, if we scooted on towards a midway site, which has the same rocks as Northeast Syrtis, or at least some of the very similar rocks, you could see potentially caching a lot more of a variety of materials that are highly relevant for studying the whole planet of Mars. And again, ultimately, the site selection was not entirely based on astrobiology. We did have to consider things like what we would learn about the geology of Mars, what are the capabilities of the instruments on the rover, and finally, what is the value and confidence that these samples will be returned, and what will we learn from them. And so Jezero falls in this interesting time period between the late Noachian probably and the early Hesperian. And if you look at row D, you'll see that this is where there was this distinction between dominant open system weathering and surface waters to like a more episodic and drying out of Mars. And so this climate change is something that occurs in the region. And finally, the dynamo during the first several 100 million years of Mars history, the evidence of either in magnetization or finding these early rocks, the oldest rocks on Mars, could be something that you could do during the mega mission or extended mission. And so these megabreccia blocks, for example, are shown in red on the figure in bottom left. And they're accessible along the way, preserving, this layered stratigraphy and possible magnetic signatures. And so we'll leave Jezero at that. There are so many questions that we could answer at this delta, but Jezero is not the only delta on Mars. Another one is Hypanis that I think might give Jezero a run for its money. And so Hypanis is a key site because it could tell us about this question of, did Mars have an ocean? And so because of this implication, I think Hypanis that's why it was one of the sites that was proposed both for an ExoMars mission and also for the Mars 2020 rover mission. And so the guiding questions from my research several years ago was, what was the climate and depositional environment like on early Mars? What processes form this Hypanis deposit? And what can the measurements here help us to understand about the global inventory of water on Mars and the past habitability? And so Hypanis also occurs along the elevation dichotomy boundary. But the key difference here is that Jezero was in a crater lake, right? Jezero had a clear inlet and an outlet where you can measure the elevation and know that the water likely ponded up at least to the outlet elevation. So that story all makes sense that Jezero is a delta and in a crater lake. But the problem with the topography around Hypanis is that there is no wall, there is no crater rim, there is nothing to hold back that water to say that it ponded. It's an open system, which means that if Hypanis formed underwater subaqueously as a delta, then that would mean that the entire northern plains of Mars was covered with water. So I'll repeat that because it's significant. If Hypanis, if you believe it's a delta, then there was an ocean. Okay, so here's what Hypanis looks like. And this is a CTX image mosaic. You can see Hypanis is this light tone deposit in the center, and it's very large, about 50 kilometers across. It also has this neighboring potential deltaic deposit known as Sabrina, which is in Magong Crater. And so just to compare some of the deltas we've talked about already, if this is the two-scale size comparison, if this is the size of Jezero, then Eberswalde is almost double or over double the size. Sabrina would be the largest delta on Mars, if not for Hypanis, which dwarfs the other deltas that we've talked about. And so how does this stack up with river deltas on Earth? Hypanis is most similar in this chart to something like the Colorado Delta, which is where the Colorado River lets out in the Gulf of California in Mexico. And so again, this question, the main question that we should be asking is it a delta? Because if so, at least the southern Crissy portion, if you can construct some sort of rim upon that water, at least 100-kilometer wide body of water existed, but likely a northern ocean. And so again, to compare and put this in perspective, how large this delta is for Mars, I'm showing here Hypanis overlaid on the greater Phoenix area. And so it covers most of Phoenix, Arizona. If you were to think of like a typical college campus, maybe a kilometer across, this is ASU, for example, would fit entirely in one of these younger channels on the surface that cuts through the surface of the main lobe of Hypanis. And when I say a young channel, what I mean is younger than 3.6 billion years old. And that's the age of the Hypanis deposit, which comes from crater counting studies and a couple other measurements. And so to put this on Atlanta, if you're familiar with Atlanta and Georgia Tech, the entire Georgia Tech campus is inside that small red circle. And so this feature is quite a bit larger and different already in morphology than some of the other deltas that have been proposed on Mars. So to come up with tests, I had to look at the Mars literature and the terrestrial literature and try to find tests that would be diagnostic of certain landforms or processes. So a lot of these come with some caveats, and these tests had to be chosen based on the fact that I was using remote sensing. Because if you're not there in person, then you can't develop the in situ tests where you actually look at grain size and stratigraphy in detail. You can only look from orbit, and in our case, Hypanis is covered with a lot of dust, which makes multispectral observation of the composition very difficult. It's experienced a lot of erosion. We think about 2 times the volume of the main lobe has been eroded. And also, we're just looking from orbit. So these were some of the tests that I came up with to get at this process hypothesis. And so I'll jump to the result and then talk a little bit about some of these tests. As you can see, I used these tests to sort of figure out which hypotheses were supported and which were not. So one of the tests that I look at was whether the beds have this diagnostic feature of a topset and foreset transition in bedding angle. And again, if you look at the example of what a delta looks like in basic form, you can see that there's a topset foreset transition, which is diagnostic of deltas, has been used for other Mars studies, and is something that you wouldn't find in the other processes that I tested, a mud flow or an alluvial fan. And so to do this, you need high-resolution digital elevation models, and you need to measure the slope of all the beds that you find. And so to do this, I had to create high-rise DEMs where they were unavailable, request stereo pairs and create DEMs. But I was also able to leverage a lot of the landing site work, legwork that had been done to create some of these high-rise and CTX stereo pairs already. And so with all of these high-resolution digital elevation models, I was able to merge them to create a regional mosaic, which was useful later for long slope profiles across the feature. And so this figure on the left shows the different resolutions of data sets in the digital elevation model mosaic that went into creating ultimately one smoother regional topographic model. And so to look at where these bed slopes might occur, one would like to look at the distal edge of the main lobe, where you can clearly find cliffs and measure the stratigraphy. Here are 3 cliffs that I looked at. I labeled them A, B, and C, but in more detail, what these cliffs look like when you're able to drape the high-rise images over the DEM is you're able to identify over 30, in some cases, individual layers. And these beds stack up to form a height of the delta between 60 and 100 meters in some case, which, if you put that in perspective with the Georgia Tech Ford building, for example, that would be taller than the Ford building. And I used tools, again, to measure the strike and dip of these beds to look for that transition. What I found was that all the beds were approximately horizontal over very long distances, and so they could be traced for over kilometers without any interruption. This really indicates a prolonged calm depositional environment. So not a highly energetic environment, but a calm environment that formed these stacks over time. And what I found was the architecture was not the same as an alluvial fan or a mud flow. Whether we found that top-set, four-set transition, though, which we did not, seems perhaps in retrospect like a poor test. And that's because there's so much erosion and dust cover at Hypanis that for a deposit this large, probably we should not have expected to find something like that, which would be more suitable for perhaps a smaller delta in better shape. So we'll mark that as inconclusive because the beds indicated a prolonged calm environment similar to a delta, but we couldn't find the top-set, four-set transition, probably due to erosion. To check for avulsion node migration, I created a CTX favorable lighting mosaic. And what I mean by that is using shadow angles at certain times of day and times of year. That's L sub S and L sub T to create a mosaic that made the paleoflow features pop the most. And so in this mosaic, I was able to find a few different avulsion nodes, suggesting that avulsion happened over this low gradient, which is really only indicative of a delta as opposed to a mud flow or an alluvial fan. Now, to look for contemporary standing water in the region, that's a bit trickier. And this is an important test to do for determining if a feature really is a delta on Mars. Because if you find other evidence that at the same time there was other features formed probably by standing water, then that would also really support the notion that it was formed subaqueously. And so one of the main points here is that the Sabrina potential deltaic deposit is very similar and probably contemporaneous to Hypanis. So to look at this in further detail, I used Themis, which is the thermal emission imaging system on Mars Odyssey. So these are daytime and nighttime temperature images, and from those you can derive the thermal inertia. And thermal inertia you can think of as the ability to conduct and store heat. Basically, rocks have a higher thermal inertia than sand. So something with a small grain size like sand that's not indurated, during the day the sand might feel really hot on your feet, but as soon as the sun sets, it gets cold really fast, while the rocks are still retaining their heat from the day. And so what does this mean for this background thermal inertia image of Hypanis and Sabrina? Well, it's clear that Hypanis and Sabrina have a very, very low thermal inertia, lower than some of the other deltas on Mars. What this means is a very small grain size, or a thick cover of something in small grain size that's not clearly indurated. And so due to the similarities in thermal inertia, but also the similarities in albedo, the apex elevation of both Hypanis and Sabrina being the same and their morphology in high rise, we can safely say that they probably are composed of similar materials and at the same time. Furthermore, there's evidence around Sabrina of things like strand lines, distal deposits of that same material along the crater rim, desiccation cracks, indicating that the landscape might have dried out. And these desiccation cracks coincide one-to-one with these clay spectral signatures of smectite clays. And so taking that into account and other regional features that had been already published, like these hydrovolcanic features, so either water, surface water, subsurface saturated layers, or ice interacting with volcanism in Liederberg crater to the north, it meant that there is likely contemporaneous water activity. But it's so hard to say for sure that it was liquid water and that it covered the whole surface at the same time. But at least there's some evidence for aqueous activity and phreatomagmatic or hydrovolcanic activity at the same time. To look for larger clasts or boulders is also quite difficult, and the best I was able to do is use thermal inertia images, again to make assumptions about grain size and rockiness, and to combine that with high-rise images to look at the finest scale for evidence of boulders or larger clasts in young channels. What I found, again, was that none of those things existed. I could not find boulders or larger clasts in younger channels, and so we marked that as a no for evidence for a mud flow. And I'm going to skip over the levees test because it was clear from our observation that we didn't find any of those features. What's interesting is that mud flows, one would really want to see a likely source for that mud flow to originate if Hypanis formed that way. And so the nearest source is over 200 kilometers away before you get any sort of relief to trigger the mud flow. And then a mud flow would have had to travel down a sinuous channel, Hypanis vallis, with a very low gradient for over 200 kilometers. And so I think it's safe to say that it's unlikely that Hypanis was formed by a mud flow. Then to check whether Hypanis could have been formed as an alluvial fan, again, I used high-rise morphology and looked at the overall architecture and whether that corresponded to analog alluvial fan architecture as seen on Earth. And of course, some of our analog studies are biased towards Death Valley fans, at least in the literature, which might not be indicative of all types of alluvial fans, especially low gradient or mega fans. But what we found was an architecture, again, that was not consistent with an alluvial fan. And so there is evidence, some, that supports the deltaic origin, but none of our tests supported the other two formation processes. So what this means is that we think that Hypanis formed first as this main lobe, which I designate as A, which was once much larger but has been eroded back. And you can see distal deposits, which are labeled E, in the north, over 100 kilometers away from A. And these distal deposits likely match what was once a very large main lobe A that has now been eroded or covered by floor material. And so to learn more about this, I encourage you to read the sequence of events in the Adler 2019 paper, but also in Peter Fodden's 2018 paper about Hypanis, which makes a really nice argument for the northeastward progression and decreasing water level here. And so after the main lobe A formed, I think that the northern lobe, which I designate B, then formed, followed by these inverted braided channels, C and D, which were reaching out farther towards a new lower water level in the northeast, as the history of water was waning and decreasing towards the northeast at this time. And so I think that, in summary, we found that there is evidence for the deltaic deposit. There is not much evidence, at least from our tests, for the other formation mechanisms. And so we support the deltaic hypothesis for Hypanis. Now, what this means is that a large body of water probably existed at least 100 kilometers if it were somehow confined just to the southern Crissy region, but likely a northern ocean. And I think that's important that we continue to study Hypanis and deltas like Hypanis, because it could tell us if Mars had an ocean, which would greatly influence most of our understanding and our future direction towards investigating habitable environments on Mars in the future. Thank you, and I'm happy to take any questions.